Hello, everyone. Thank you for joining. It is right on the hour. It is 1 o'clock Eastern, and we were just going to get started right on time. And I'll do a couple of housekeeping items here. My name is Carrie Lang. I'm the Agency Development Coordinator at National Flood Services. We want to thank you all for being here today. I'm going to be admitting a couple more people as we get started. This presentation today is about 40 to 45 minutes, and we'll allow some questions after. We are recording this webinar, so we'll have it posted on our National Flood Services website next week. And if you could do us a favor and just make sure that your audio is muted. Like I said, if there are any questions, feel free to stay on so Dr. Phil can answer any of your questions. I'm going to stop sharing. And I will let our expert here, Dr. Phil, you can go ahead and share your screen while I do a little bit of an introduction for you. Thank you again for being here today. So our expert today is Dr. Phil Klotzbach. This is the second time presenting with National Flood Services, and we're so happy to have you back. Honestly, it's a real pleasure working with you. You make it really easy to set all this up, so I really appreciate that.
Thanks, Carrie.
You're welcome. I did have his bio up on the holding screen, but just as, and I'm sure Dr. Phil, you'll go over this, but just as a little bit of background, Dr. Klotzbach is a research scientist in the Department of Atmospheric Science at Colorado State University. He's received his PhD in Atmospheric Science from CSU in 2007. He's worked in the Department of Atmospheric Science for the past 20 years and was a co-author on the Atlantic Basin Hurricane Forecast with Dr. William Gray through 2005. And I will hand it over to you.
Thanks, Carrie. Thanks, everyone, for tuning in. Feel free to also, if you have questions during the talk, if you can type them into the chat. Sometimes that's a good way to keep them or to get them out there early, such that when we go through at the end, the questions are already out there. But as Carrie mentioned, we're going to spend some time today talking about Atlantic Basin seasonal hurricane prediction. We'll do a look back at 2020, obviously talk about what we're expecting for 2021, and talk about some longer term trends that we are observing when it comes to hurricanes and climate change. So to begin with, we're going to start with a little bit of an introduction, basically how we go about doing seasonal hurricane forecasts. We'll spend most of the time talking about, or we'll spend a little bit of time talking about what happened last year. Obviously, we'll spend quite a bit of time talking about what we expect to see for 2021. And then again, look at some longer term trends in overall hurricane activity, as well as trends in landfalling hurricane activity, especially for the continental United States. But whenever I do talks on seasonal hurricane prediction, I always like to start by talking about the great contributions made by Dr. Bill Gray, who is the founder of the seasonal hurricane forecast. He's the first person to do seasonal hurricane predictions for the Atlantic Basin. So CSU, we've been doing seasonal hurricane forecasts all the way since 1984. So Dr. Gray, in addition to founding the seasonal hurricane forecast, made fundamental contributions to tropical cyclone genesis, structure, intensity change, just a giant in the field of tropical meteorology. His papers are cited hundreds of times every year. In addition to pioneering the seasonal hurricane forecast and all this other research, he was also a mentor to over 20 PhD and 50 master's students, and just a giant in the field of tropical meteorology. And certainly his contributions are greatly acknowledged, and he's certainly sorely missed. He was very passionate that the seasonal hurricane forecasts continue after his passing in 2016. Dr. Gray was also a huge fan of baseball, and one of his favorite philosophers was the great Yankee catcher Yogi Berra, who once stated that it's tough to make predictions, especially about the future. And I think certainly whether we're talking about Atlantic hurricane seasonal activity, whether we're talking about weather predictions, whether we're talking about sports predictions, forecasting the future is tremendously difficult. But another statement by Yogi Berra, I think, is really prescient when it comes to seasonal hurricane prediction, and that is that you can see a lot by looking. Basically, by going back into the past and looking at historical weather and climate patterns, it can teach you a tremendous amount about how active the upcoming season is likely to be. So, for example, we know which years in the past were active hurricane seasons, and we know which years in the past were inactive hurricane seasons. This data actually goes back to the mid-19th century, but it's pretty reliable, going back in the Atlantic probably to around 1950, with even greater reliability since about 1980. So then what we do is we look for precursor signals, basically what sets of climate conditions preceded active seasons in the past, and alternatively, what sets of climate conditions preceded inactive seasons in the past. And what you find is that there tends to be one set of recurring climate conditions before active seasons and the opposite set before inactive seasons. And I think the easiest way to view this is to look at climate conditions during the peak of the Atlantic hurricane season. The Atlantic hurricane season peaks in September. Most of your hurricane activity in an average year occurs between August and October. And if you look at the 10 most active hurricane seasons since 1950 and difference them from the 10 least active Atlantic hurricane seasons since 1950, during August through October, you find in general warmer water in the Atlantic during more active seasons. That makes sense since hurricanes live off of warm ocean water. More warm ocean water provides more fuel for developing tropical storms and hurricanes. It also tends to be associated with lower pressures and a more unstable atmosphere, both of which also favor a more active Atlantic hurricane season. Alternatively, when you look in the Pacific Ocean, you see a cold blob in the eastern and central tropical Pacific. That is indicative of La Nina conditions. La Nina is basically the opposite of El Nino. And so when you have La Nina conditions in the tropical Pacific Ocean, the question is, why would something going on in the Pacific Ocean impact hurricanes in the Atlantic Ocean thousands of miles away? And it was found by Bill Gray and others that it was due to changes, especially in winds at high levels in the atmosphere, say 20 to 30,000 feet. So typically in the Atlantic, your low-level winds blow out of the east. These are the trade winds. And at upper levels, they blow out of the west. So if you think about this in the vertical, you have what's known as shear, basically winds at low levels blowing one direction, winds at upper levels blowing another direction, and too much shear is detrimental for hurricanes. It tends to tear them apart. And in an El Nino year, you tend to get very strong upper level westerly winds that tear apart hurricanes. Alternatively, when you have La Nina conditions, you tend to have weaker vertical wind shear, and you tend to have conditions that are much more conducive for hurricanes to be able to develop and thrive. And certainly, as we saw in 2020, we had an extremely active hurricane season, and that was associated with a moderate strength La Nina event. And we're going to spend a little more time now talking about what happened last year, and then obviously we'll then move in and talk about what we expect to see for the 2021 Atlantic hurricane season. So first of all, looking back at 2020, it was an extremely active season. And I think one thing about 2020 is that the season just keeps on giving. Even though the hurricane season officially ended on November 30th, we've had a couple of storms actually get upgraded since the end of the season. So after every hurricane season, the National Hurricane Center goes back into the past, goes back to the past year and looks and sees, okay, did we get any observations after the storm went by that will help us give us better idea as to how strong it actually was? And so the Hurricane Center will assess the storm's intensity in real time, but then they'll use this time in the off season to go back and look at all the storms and see if maybe the storm was a little bit stronger or weaker than what was anticipated. And so in 2020, they actually upgraded two storms. Gamma was upgraded from a tropical storm to a hurricane, and Zeta was upgraded to a major hurricane right before it made landfall in the state of Louisiana. So overall, last year ended up with 30 named storms, which was the most on record, breaking the old record of 28 set back in 2005. We ended up with 14 hurricanes, including Gamma's upgrade. That's the second most on record, trailing only 2005. And we ended up with 7 major hurricanes. Those are hurricanes with winds of 111 miles per hour. Winds are category 3 or greater. And we were tied for the most on record with the 2005 hurricane season. We also can look at accumulated cyclone energy, which is an integrated metric that accounts for the frequency, the intensity, and the duration of storms. And that value was also quite high this past year, but ACE wasn't quite as high. You see, we only ranked 6th most in the satellite era since 1966. And that's because ACE is a measure of a frequency, intensity, and duration. And while we certainly had tons of storms last year, and a lot of them were very intense, most of these storms formed in the Western Atlantic, and consequently, they didn't necessarily have a very long duration time. A storm like Hurricane Irma in 2017 that developed right off of Africa and tracked all the way across the Atlantic basin, these are the storms that generate tremendous amounts of accumulated cyclone energy, or ACE. But just to kind of give you some perspective on what 2020 look like compared with historical seasons, you can certainly see a tremendous amount of storm activity last year. Here's the record going back all the way to 1851. Obviously, as you go back in time, the data gets less certain. We didn't have satellite data prior to the mid-1960s. We weren't flying airplanes into the storms prior to the mid-1940s. And consequently, some of these earlier storms back, especially prior to 1950, are likely underestimated. But this gives you an idea of just how much 2020 was. It was an extremely active season, ranking number 1 or number 2 for most parameters, at least since 1950. And so really one of the things that really stood out about 2020, in addition to how much storm activity it had, was just how much storm activity there was in the western part of the basin, especially 7 degrees west, 70 degrees west, and farther west. And if these storms form and intensify in the western part of the Atlantic, that's really bad because there's basically no place that they can go that they aren't going to cause significant levels of damage, whether they make landfall in the United States, the Caribbean, or in Central America. And certainly, obviously, the US was extremely active last year with 6 landfalling hurricanes and 11 total storms making landfall. And obviously, especially late in the season, hurricanes Eta and Iota, basically a double whammy, causing tremendous amounts of damage in Nicaragua, Honduras, as well as Guatemala. So why was 2020 so active? Well, there were a couple of factors, as you might recall from the figure that we looked at earlier, showing what makes active hurricane seasons. 2020, as you would expect, had conditions pretty similar to what we expect for a very active hurricane season. Waters in the Western Atlantic, Caribbean, even into the Central Tropical Atlantic were much warmer than normal. And in the tropical Pacific, especially in the eastern and central part, they were colder than normal, indicative of a La Nina event. And as you would expect with the La Nina event, colder waters in the eastern and central tropical Pacific Ocean tend to be associated with lower levels overall of vertical wind shear. So you have less of these winds tearing apart hurricanes. And consequently, we saw, as you would expect, a very, very active hurricane season last year, especially active in the western part of the Atlantic basin and into the Caribbean. So one of the things that we saw a lot of last year was these storms that rapidly intensify. And rapidly intensifying storms are storms that intensify by 35 miles per hour or more in 24 hours. And so if you look at this figure since 1950, you can see 2020 really does stand out. The most rapid intensification events on record. We'll talk a little more about rapid intensification as we talk more about climate change and its potential impacts. But certainly rapid intensification was one of the big stories of the 2020 hurricane season. And obviously, if rapid intensification happens in the middle of the open Atlantic, it's not that big of a deal. But when it happens in the Western Atlantic, it can be a huge deal because you have storms intensifying right up to or almost up to the point of landfall. And obviously these can cause tremendous amounts of damage. And certainly that's what we saw last year. And in terms of from a warning perspective and a planning perspective, if storms are rapidly intensifying up to or almost up to the point of landfall, that can pose extremely problematic for getting the population ready for a particular storm event. And you can see of the 10 storms that underwent rapid intensification last year, 8 of them did so in the Western Atlantic up to or almost up to the point of landfall. And again, that can obviously pose extremely problematic from a preparation and mitigation perspective. But while 2020 was extremely active and very extremely active for landfalling storms, one of the things is 2020 really could have been a lot worse. And the reason is because obviously, as I learned in one of my undergraduate geography classes, it's all about location, location, location. And what we didn't have last year were storms making landfall in densely populated areas. Most of the storms made landfall in relatively sparsely populated parts of the coastline. Obviously, especially Hurricane Laura delivered a very significant blow to Lake Charles, but had Laura made landfall 100 miles farther west and it hit Houston and Galveston head on, obviously the damage could have been so much worse. So while it was an extremely active season, especially for Louisiana, the damage could have been much, much worse, as well as the loss of life would likely have been much worse had several of these storms made landfall in more densely populated parts along the US coastline. So while it was an extremely active season, the US really did dodge a bullet in terms of where these storms made landfall, not making landfall in densely populated parts of the United States coastline. But that's 2020. Obviously, now we want to move ahead and talk about what was likely in store for the 2021 Atlantic hurricane season. We put out our first update last month, or first forecast last month. We'll be updating it shortly on the 3rd of June. So with the early April forecast, we're calling for a total of 17 named storms. Of those 17, 8 becoming hurricanes, and of those 8, 4 becoming major category 3, 4, and 5 hurricanes. Again, we have that integrated metric known as accumulated cyclone energy. It is also above its long-term average. You may have heard NOAA actually upped their long-term average. They formerly used 1981 to 2020. At the start of every decade, they up it to the next decade. So the 1980s fell off, the 2010s came in, and since the 2010s were more active than the 1980s, the official average season is now a little more active: 14 storms, 7 hurricanes, and 3 major hurricanes. So while we're forecasting an above normal hurricane season, we're not forecasting the levels of activity that we experienced during the 2020 Atlantic hurricane season at this point. We're forecasting an above normal season, but not as much activity as was experienced in those years. We have several techniques that we use to come up with our final forecast. One is a statistical model, and this statistical model uses techniques similar to what was used by Dr. Gray back in the early 1980s. And this is, again, using historical weather and climate data to forecast upcoming hurricane seasons. And so these 3 parameters, 2 of them are kind of assessing the large scale conditions in the Atlantic Ocean. One is in the Pacific Ocean, trying to basically assess what's going on with El Nino. These 3 predictors in combination can explain a considerable amount of the variability in overall Atlantic hurricane activity. Now, there's obviously a lot that can change between April 1st, when this forecast is prepared, and June 1st, when the season starts, and August 1st, when the season really ramps up. Over 90% of all your major hurricane activity occurs after the 1st of August in an average season. But you can see in this plot, the forecast model does a reasonably good job. There are some years where the forecast busts, but in general, the forecast does a reasonably good job at capturing the variability. You'll see the correlation is 0.66, implying that you can get about 40% of the variability with this early April statistical model. That, again, still leaves you about 60% of the variability that's unexplained. Some of it is because with seasonal forecasts, you're never going to be able to explain all the variability. And a lot of it, too, is you're still several months prior to the season really ramps up around the 1st of August. So in addition to this simple statistical model, we also are using what's known as a statistical dynamical model. And the way that this statistical dynamical or hybrid model works is we forecast the large scale conditions later on during the year, and then use the relationships between those large scale conditions and Atlantic hurricane activity to dictate the forecast. So here are the parameters that typically go into our early August statistical model. They look at July large scale conditions over various parts of the Atlantic basin. Now, I would love to know now what July is going to look like, but obviously we don't because we're not to July yet. But you can use a climate model to forecast what July is going to look like. And these climate models are built on about 40 years of historical data to better be able to calibrate these models so they work well in forecasts upcoming. And so if you look at this plot here, this shows the forecast from the statistical dynamical model compared with the observations, and you get a similar correlation. The statistical model was 0.66. The dynamical model is 0.62. And then if you just simply do an arithmetic average of these 2 forecasts, you get a correlation of 0.7. So you can get from about 40% of the variability with a simple statistical model up to about 50% of the variability when you simply just average the statistical model and our hybrid model. So this is encouraging and is one of the reasons why we're more confident in our April forecast now than we were, say, even 5-10 years ago when we didn't have these additional tools to help with our seasonal forecast. In addition to the statistical dynamical model, we also use analogs, and analogs involve going back into the past and looking for years in the past that had conditions most similar to what we currently see and what we expect to see for the peak of the Atlantic hurricane season. And so you can see our 5 analog choices are 1996, 2001, 2008, 2011, and 2017. Now, these analog years are selected simply based on how similar they are overall to what we expect to see for the 2021 season. They're not based on how the storms are going to be steered. So just for example, since 2008 is an analog, doesn't mean we're necessarily expecting to see Hurricane Ike in 2008. Certainly we hope not. But to give you an idea of what we're looking for with these analogs, we have a couple of different factors. We look at water temperatures in the tropical Atlantic and in the subtropical Atlantic, and you can see in general, they're warmer than normal, and that's what we expect for the peak of the season. And also, we don't necessarily expect to see a La Nina event, but probably what's known as cool neutral conditions, so colder than normal, but not quite up to the La Nina threshold. In addition to the seasonal forecast and the overall raw numbers, we also now provide probabilities of exceedance. And the reason that we do this is to provide kind of better quantify the skill of the forecasts. And so here in the blue bars are the probabilities of each year exceeding a specific set of hurricanes. And the red numbers are the red columns are what we expect for 2021. And as you can see, the red columns in general are higher. And that's simply because we're forecasting an above normal season. So the odds of having an above normal number of storms also increases. So basically what we do is we fit the historical error of the models to a statistical distribution and then calculate the probabilities of various hurricane numbers from that. So our forecast, we forecast hard numbers, but we also obviously recognize the uncertainty. So we basically calculate uncertainty ranges using these probabilities of exceedance. And we do this for all of our different parameters. And you can see that when we do these probabilities of exceedance and we do these uncertainty ranges, they're pretty similar to what you get when you look at NOAA's seasonal hurricane forecast, which is actually going to be coming out this Thursday. So our forecast is for a total of 8 hurricanes in 2021. And the uncertainty range is between 6 and 10 hurricanes. So what are the large scale conditions? Why are we forecasting an above normal hurricane season? There's a couple of primary factors. One is we're still dealing with a fading La Nina. It's officially now been declared neutral, and that's in that blue box rather. And then the red box, you see near average water temperatures across the tropical Atlantic, but you see a lot of warmth in the subtropical Atlantic, and I'll spend a little bit of time talking about why that subtropical Atlantic warmth is critical here in a couple of minutes. But first, let's focus on the tropical Pacific. NOAA officially declared La Nina over a couple of weeks ago. And now that La Nina is over, we're now in neutral conditions, which means neither El Nino nor La Nina. So right now we have near average water temperatures across the eastern and central tropical Pacific. At least as of now, the odds of this transitioning over to a La Nina event for the peak of the Atlantic hurricane season, so August through October, highlighted by the black arrow, is extremely low, less than 10%. So right now, we're favoring the neutral scenario, so probably neither El Nino nor La Nina for the peak of the season. You can see NOAA still has a fairly high probability of a La Nina event, a little bit over 40%. So consequently, this is one of the reasons why we're forecasting an above normal season, is we don't expect to see an El Nino event for the peak of the 2021 season. So there's a variety of different models that forecast El Nino and La Nina. This plot should be updated this coming Thursday. If you like climate models and you like acronyms, this plot is for you. You can see there's a whole pile of different models that forecast El Nino versus La Nina. And you can see that most of these models for August through October are calling for near average water temperatures, maybe a little bit below, but all in all, cool neutral to perhaps weak La Nina conditions seems like the best bet for the peak of the 2021 Atlantic hurricane season. Obviously, there's still a lot that can change, which is one of the reasons why we update our forecast. Again, our next forecast update will come out on the 3rd of June. So now switching gears and focusing on the Atlantic Ocean, you can see again, water temperatures in the deep tropics, so south of 20 degrees north to about 10 degrees north, is about near average. But if you look at the subtropical Atlantic, you see much warmer than normal waters there. And even though the hurricanes obviously do track through that region, the main reason we're interested in that region at this time of year is because lower pressure or warmer waters in the eastern and central subtropical Atlantic tend to be associated with lower pressure. And if you have a weaker subtropical high, meaning lower pressure there, it tends to make weaker winds blowing across the tropical Atlantic and Caribbean, causing less churning up of the ocean surface. And consequently, then the tropical Atlantic tends to warm for the peak of the season. So that's something we're going to be closely monitoring with our forecast update here in a couple of weeks. But you can see really why we focus on the eastern subtropical Atlantic is because that's where the correlations are the highest. Here's a plot showing correlations between accumulated cyclone energy, this integrated asymmetric, along with sea surface temperatures. And you can see just how high the correlations are in the eastern part of the Atlantic basin. So right now, the Atlantic, I would say, looks favorable for an active hurricane season, but there still is some uncertainty. Obviously, we could get a surprise El Nino, although the odds of that seem fairly low. In addition to the forecast from our group, there are forecasts from a wide variety of other groups as well. Here's a forecast from the ECMWF, or European Center for Medium Range Weather Forecasts. And this is a forecast for sea surface temperatures. So you can see in general, the model is calling for warmer than normal sea surface temperatures in the Atlantic and colder than normal water in the eastern and central tropical Pacific, indicative of perhaps a La Nina or at least a weak or cool neutral ENSO event. And so when you put these two predictors in combination, you would expect the ECMWF to be forecasting an above normal Atlantic hurricane season, and they are. Here's the latest forecast from the ECMWF. they're forecasting a total of 9 hurricanes, while the average is about 7. So in these climate models, you not only forecast large-scale things like El Nino and La Nina, you can also forecast things like tropical cyclones. The model will spin up systems that look like tropical cyclones, and you can simply count how many of those the model is forecasting. And that type of approach gives you reasonably good skill, although there certainly are cases where the statistical models or these statistical dynamical hybrid models actually yield you more skill. So in addition to basin-wide activity, we also do probabilities of United States landfall and as well as Caribbean landfall. And you can't say months in advance when or where storms are going to strike, but in general, more active seasons have more landfall and hurricanes. So here on the right-hand side in parentheses are the climatological average values or the long-term average values, while the numbers just to the left are the probabilities for 2021. And the reason these probabilities are higher than normal is because we're forecasting an above normal hurricane season. Consequently, the probabilities of landfall also go up. And again, we do this for the East Coast, the Gulf Coast, as well as the Caribbean. But something new that we're doing this year is we're not only doing landfall probabilities, we're also doing probabilities of being impacted. And the way that we define an impact is that a storm tracks within 50 miles of your particular landmass. So basically what we did is we calculated this for every county along the coast from Texas to Maine. We counted the number of storms. And then what we did is we used a 50-mile radius. And the reason that we used a 50-mile radius is because a storm doesn't have to make landfall in your county to cause significant impacts. And you can have storms that make landfall hundreds of miles away that still cause significant impacts if the storm, say, is still a tropical storm or hurricane strength. And consequently, we can see here, obviously, this Plymouth County, which is where I grew up, only had 14 hurricanes track within 50 miles. So consequently, the probabilities of getting a storm there in any particular year are low. But one thing we always emphasize is that you're not due or not due, basically. So you can be due or you're not. There's no rhyme or reason to hurricane landfall. So if you have a hurricane landfall one year, doesn't mean that you're more or less likely to have a landfall the following year. But even in Massachusetts, we had 14 storms over the course of 170 years. 2 made landfall just a couple of weeks apart, Carol and Edna, back in 1954. So again, we do this approach for every county and parish, as well as every state, as well as Canadian provinces, Central American countries, and Caribbean islands. So here's an example for the state of Florida. The probability of one hurricane or more hurricanes within 50 miles of the state of Florida, on average, is about 60%. This year, it's at 75%. Also, with major hurricanes, on average, it's about 40%. This year, it's 28%. So the probabilities, again, are elevated because we're forecasting an above normal hurricane season. As I mentioned before, these forecasts aren't stagnant. We'll be putting out an additional forecast on the 3rd of June, another one on the 8th of July, and a final forecast on the 5th of August. And as I mentioned before, even though the June forecast comes at the start of the season and July and August are 1 and 2 months into the hurricane season, respectively, over 90% of all your major hurricane activity occurs after the 5th of August. So consequently, we want to have one last update that gives you the best idea of exactly how much storm activity you're likely to have for the upcoming hurricane season. If you can't get enough of seasonal hurricane forecasts, I invite you to check out seasonalhurricanepredictions.org. It's a website that's put together by our group at CSU, primarily sponsored and run by the Barcelona Supercomputing Center with some funding from AXA XL. And you can see all the logos of all the different groups contributing their seasonal forecasts to this website. They include government agencies, private sector weather companies, as well as universities. So if you click on the website, you can get an extensive amount of information, including the various seasonal forecasts from the different groups. Blues are from universities, purples are from private sector weather companies, and reds are from government agencies. So you can see the different groups that have done seasonal forecasts so far for the 2021 hurricane season. We're up to 15 different groups that have already submitted their seasonal hurricane forecasts. NOAA will be putting out their first seasonal hurricane forecast on Thursday. So consequently, please pay attention for that. I'll certainly be watching and seeing what they're forecasting for the upcoming season. On this plot too, the orange dot represents the average of all of the forecasts to date, while the red dot delineates the observed values to date. So thankfully, so far, no hurricanes have been formed in the Atlantic Basin. And now to conclude, I want to spend a little bit of time talking about some longer-term trends in hurricane activity. And these are longer-term trends, not just for the Atlantic Basin, but actually for some global storms as well. And so what I want to start with is by looking at trends in continental United States damage. And this is damage adjusted for inflation. So you can see this huge increase in damage since 1900. And the question becomes, well, why is that increase in damage there? Is this a climate change signal? Is this demographic changes? Is there some sort of strange atmospheric ocean variability that's causing this? What's going on to make these numbers go up as much as they are? But obviously, to do this, we know there's been changes in population along the coastline, so we need to adjust for those when we do our analysis of the damage. So we have 35 million people, more people in coastal counties since 1900. And you can see just the huge number of people that moved into South Florida on the west coast near Tallahassee, Long Island. Large population growth as well in parts of Mississippi, Alabama, Louisiana, and into the peninsula of Florida as well. So there's a lot of people that have necessarily not experienced a significant hurricane that just moved to Florida. So consequently, we want to be able to kind of keep people focused on what exactly is going on. In addition to more people in coastal counties since 1900, we also find there's been a growth in the number of housing units. Since 1940, we've seen 18 million new housing units in coastal counties. Obviously, that makes sense because you've got a lot more people living along the coast. You got to have houses for them to live in. So we have this large growth in population, a large growth in housing, large growth in exposure along the coastline. And this is some research we published a few years ago, back in 2018, focusing on basically what's happened with the damage, what's happened with the landfalls, and basically what's causing the increases that have been observed so far and what might be happening in the future. So we have this growth in population and wealth. And so next what we want to do is basically do a normalization. So basically take into account the storms that have formed and the numbers, or the storms that have made landfall in the past and the damage that those caused, and then look and see how much damage those storms would cause if they made landfall today. And so as an example, we're going to look at the 1926 Great Miami Hurricane, a Category 4 hurricane, large Category 4 hurricane, slammed into downtown Miami back in 1926. In 1926, the storm caused about $80 million in damage. But in 1926, if you look at the figure on the left, you can see not much going on in Miami in 1926. The population of Miami-Dade County, only about 100,000. Now the population is 2.7 million. So there's been a huge growth in population along Southeast Florida. And consequently, this storm, if it were to make landfall today, is estimated to do over $200 billion in economic damage. Now, there are some things we can do to potentially ameliorate that damage by building better, by building stronger, and certainly in South Florida, they do have fairly robust building codes that may help reduce some of this economic damage in the future. But certainly we need to take into account this growth in population, growth in wealth, along with inflation when we try to assess basically long-term trends in damage. So if you normalize the damage for all of these storms, you can see the big spike in 1926 from the Great Miami Hurricane. You also see a big spike in 1900 from the Galveston Hurricane. Excuse me, you see some other big years in the 40s and 50s. And then you see a lot of years lately, and obviously 2005 stands out, 2017 stands out. And so you can see, just how much damage these storms can cause. But long-term, you don't see any trend in the normalized damage from hurricanes back to 1900. And that matches up pretty well with just looking at the overall number of landfalling hurricanes in the continental United States. There's no long-term trend, and we don't see a trend for major hurricanes either. So since we don't see a trend in these indices, we wouldn't necessarily expect to see a trend in the damage when you properly normalize these hurricanes for how much damage that they would have caused had they made landfall, or had the storms that made landfall in the past made landfall today. But obviously, the fact that the damage is going up is also critical, and it's something we need to take into account, both as meteorologists as well as the insurance industry, because with this increases in damage, obviously does cause increasing other challenges when trying to rebuild after these storms. But when it comes to climate change, one thing we are seeing in general is more storms undergoing rapid intensification. So storms intensifying by 35 miles an hour or more in 24 hours. I do want to point out here, though, that some of these rapid intensification events excuse me, in the 50s and 60s may have been underestimated a bit, just simply due to the fact we didn't have the satellite data was either dodgy or not, or we didn't have any, and the aircraft were not flying as often as we do today. But we still likely would see a little bit of an increasing trend in rapid intensification. And that's because in general, when you have a warmer water temperatures, that provides more fuel for storms. Now, it's not as simple and straightforward as just knowing warmer water means more hurricanes. It's also basically how the temperatures warm throughout the atmosphere. In a climate change scenario, you warm temperatures at the surface, but you also warm temperatures throughout the atmosphere. And consequently, if you look over the entire period of record, you might not necessarily see huge increasing trends just because the increasing upper level temperatures increase the stability of the atmosphere, and that can tend to take off some of the edge that you get from just the overall warming sea surface temperatures. We do see a slight or somewhat of an increase in global Category 5 hurricanes going back to 1990. And the reason that we look back only to 1990 is because as you move farther back in time, the data just gets dodgier, and it's harder to know exactly if we were observing the storms as well as we do. We certainly weren't observing the storms as well as we do today. So we're a little less certain about what the overall intensities of these storms are. But if you go back to 1990, you can see overall there is an increasing trend in global Category 5 hurricanes. So kind of with climate change, we don't necessarily expect to see more hurricanes. We may actually get fewer overall storms, maybe even fewer hurricanes, but that the storms that do form have the potential to reach somewhat higher intensities, given the overall warmer waters, although the increase in upper level temperatures may take away some of that ability for these storms to grow stronger. But I think sometimes the focus on climate change and hurricanes kind of gets skewed away from where we really should be focusing. And I think one of the big areas we can focus on is increases in sea level rise. So sea level has been going up back since 1900, but you can see sea level rise in general has been increasing at a higher level in the last couple of decades. And as that increasing sea level rise, even though 4 millimeters a year doesn't sound like much, when you consider 4 millimeters a year, you consider that in decades and centuries, that becomes a decent amount of sea level rise. And obviously, even a sea level rise of a few inches can cause significant inundation levels beyond what we're currently seeing. And that's because obviously there are certain parts of the coastline that slope up very gradually. So 6 inches or a foot of sea level rise can mean the water penetrating much farther inland when you get the wind-driven storm surge associated with these hurricanes. And we do see the sea level rise increasing in the past few years as the oceans continue to warm. An additional challenge we have with sea level rise, and additional challenge we have with global climate change is that as you have a warmer atmosphere, you're likely to see more rainfall. Warmer atmosphere can hold more moisture and can therefore yield more rainfall. And it doesn't necessarily mean that every storm is going to be producing more rainfall than the storm before it, but when you get these slow moving storms like Harvey or Florence or Imelda, they can drop even more rainfall. And obviously when it comes to damage from storms, it's not just the storm surge and the saltwater flooding, it can be the freshwater flooding. And this freshwater flooding can also extend fairly far inland. And so this is kind of the information that I wanted to draw your attention to, is that, a lot of the focus gets on, are we going to see more storms, or are the storms going to be stronger? And my biggest concern is more with some of the water impacts, both the increases in sea level rise, as well as overall rainfall totals, just because a warmer atmosphere can hold more moisture. There's also some research that's been done basically trying to argue that storms may move also slower in the future. And obviously slower moving storms spend a longer time period over a small area, and consequently also bring more rainfall. So this is another concern that we're going to be focusing on pretty closely as we move on down the next few years and decades. So with that, I'd like to thank you very much for your attention, and I'll try to answer any questions. So thank you.
Thanks, Dr. Phil. So we had one question in the chat while you were presenting, and it was closer to the beginning of your presentation, and it is there a way to adjust form observation bias specifically before the satellite era?
Yeah, that's a really good question. And there's a lot of work that's been done on this. And so, when it showed this data set going back to 1851, we all know how we're observing hurricanes now is a whole lot better than we were observing them in the later part of the 19th century. And we actually were just working on a paper on last year. And one of the little pieces that we put in there was addressing basically how some of the observational platforms have changed with time. So in the late 1870s, we started observing hurricanes better. The U.S. Signal Corps started basically monitoring these storms closer. We started having telegraphs, so you could basically communicate from the ships to surface in a much better manner. And then you started having more issues with, once you started getting the aircraft started flying into storms in the 40s, but they didn't necessarily fly all that often. They started flying more often in the 50s and 60s, and the satellites, even now our satellites are so much better than they were in the 70s and 80s, much higher resolution, much clearer. So all this to say, there has been some work trying to basically tell we may have missed in those prior years, using basically ship traffic and trying to estimate how many ships would likely have encountered these storms. And so there are some ways of trying to adjust for these observational biases, but a lot of times when we look at trends, we'll start in either say 1950 where the data is reasonably good, or even a little bit later, say 1980 when we have pretty good data. But the Atlantic has kind of these sharp ups and downs in overall hurricane activity that occur on 20 to 30 year timescales. So we try as best we can to to adjust for some of these observational biases. There's been some papers published that have tried to argue and say, okay, maybe we missed 1 or 2 hurricanes, going back in time. And even in the last, say, 20 years, we're certainly naming more storms now than we used to. Now, these aren't necessarily hurricanes, but these are weak, short-lived storms, and that's just due to improved satellite data that allows us to be able to detect the warm centers of these hurricanes that we didn't necessarily know were there even 20, 30 years ago. And we also have some improved diagnostic techniques that really help us understand what is a tropical storm or a subtropical storm and what isn't. And so consequently, even since 2000, we're probably naming about 2 more storms per year than we would have named prior to that time.
Great, thank you. Santiago, I hope that answered your question. There weren't any other questions that came in the chat, but we have some time to, if anyone feels comfortable, they can unmute, put something in the chat. Feel free to ask any questions. And I will, this is being recorded, so we'll go ahead and put this on our site. And Dr. Phil has been nice enough to provide his presentation to us. So we'll send out a PDF to everyone who actually registered for this presentation. Oh, great. Okay, I don't think we have any other questions in the chat. We can give, if you think of one, Dr. Phil, I love your Twitter. So, he's got all of his information on here. So if you have any questions specifically for him, if you want to come through me, like I said, you're really great to work with. And I'm so happy that you were able to come back. It's awesome to get this information and just hear you're the expert in the field in this circumstance. So it's been fun to work with you, and we're glad that you were able to come back.
Thanks, Carrie. And like I said, my contact info is here. So if you have other questions, feel free to drop me an email. And I do post quite a bit of content during the season on Twitter.
Awesome. You're getting a lot of thank yous in the chat. So thank you for being here, and everyone have a great rest of the day.
Thank you. Bye-bye.